The thing that we'd like to do is to continue with the lower limb prosthesis. If you would like to work in this field, it's either sales, or you're doing testing and calibration. You can be working with a physical therapist to train them how to use the product, but most of the time we will be doing sales or we're going to be doing testing and calibration. There are several levels of amputations, and what we want to do in this class is just to learn the terminology for these amputations. We have partial foot. Any part of the foot is amputated, that's called partial foot. Anything that is a cut on a joint, we call it disarticulation. So you'll have ankle disarticulation, where the entire joint is used to do the amputation. And then you will have transtibial, which is below the knee, right? So you have part of your tibia and fibula, and then you have the knee disarticulation. The knee is gone. So we don't like to do the disarticulations on the joints because that is going to be difficult for us to have a residual limb to have the socket on. The joints are very important for ambulation. Doing this articulation on the joint is really something drastic. Transfemoral is something on the femur, in the middle of the femur. This is the knee disarticulation here on this one. Because we cut on the knee, the surgeon will do that. This is transfemoral because we have part of it. And you would like to keep muscles and bone. And the surgeon needs to be actually very skillful in order to be able to make sure that we have some functioning tissue to use. Hip disarticulation, that's one of the drastic ones that you cut on the hip joint. The most common ones are transtibial, which is the mid tibia, and transfemoral. Our job, we don't want to do some traditional understanding of prosthesis. What I want from you to have a discussion. What can we do to include more technology in the products that we are going to be discussing? So traditionally, for lower extremities, we use basic components that include the socket, and the socket is the part that is going to be encompassing the stump or something called the residual limb. In order to secure the socket, we usually use something called gel. And the reason why you will have a gel there is just you want to reduce friction with the socket, and also that you don't want to have ulcers, pressure ulcers. And then we have a suspension system. Now this is very important. Let's say we have hip disarticulation and you want to secure it. So there is no reason or there is no use of a prosthetic that it's not secure in the body to use it, right? The larger the amputation part of the body, the more stability you need in this system. And this is usually a rigid belt, and we call it suspension system. There are a lot of ways to design this, and all of these are biomedical engineering problems because they interact with the biological living system. Then if we are talking about a hip disarticulation, you need the knee joint, and this is an artificial joint. There are a couple of types and names for them we need to know. And then you have the shank, and we call it the pylon. And you have in this shank, you could have it exoskeleton or endoskeleton, and we're going to talk about these two types. And then you have the terminal device, which is the foot. And these are all the parts of the entire transfemoral. Let's say transfemoral, you have part of the femur that can be placed inside the socket. Now, here's the thing. For us as engineers, this has been there for a long time. What we would like to do is what kind of sensors, that's the key point, sensors that we can add to these systems to make them safer, more capable, and you need to have more control. The subject needs to have more control on these devices. And we're going to talk about this. We have a couple of students and also another fellow from outside. They have lower extremities prosthesis, lower extremity prosthesis, and they said they are willing to volunteer to come with us to the lab and use the force plates. Because I would like to look at the distribution of loads. I wanted to think technology, right? This is what we have, the gold standard, but we would like to move forward. Now, you can have the same parts with the upper extremities, but in the upper extremities, remember that you need more functionality. Lower extremities is about gait and walking, but upper extremities, you need the end effector, the terminal device, in order to be able to hold and do some kind of occupational tasks. And that's important for us. Now, the socket, the knee joint, the shank and the foot ankle, and I'm presenting here traditional types. So the socket, they call it silicine bandage, band-aid, whatever that, and then you have the pelvic pill. This is what I know about most of the time. This is used if you want to have the suspension system on the thigh, right? I like to have it on the waist because that's much more stable for you. And the worst case scenario is that your suspension system fail and then the subject falling because that fails, and then you have more complications of the subject. Now, for the knee, we have multiple types. You have something called single axis constant friction knee. So it's knee that moves in one axis, rotate in one axis. So this is, do you remember this plane, the sagittal plane? So the movement of the joint is on the sagittal plane, and it is around the frontal axis, right? So this is our frontal axis, and it moves like this. And it has friction in order to make it hard, so you don't want to have it loose. But that's still, this friction is uncontrollable. It's just however you are tightening it for the subject. So the range of motion is limited by your choice as an engineer. And then you have something called safety knee. And the safety knee, we discovered that if you have these knees, the single axis knee, the knee will flip on the other side. So we started having something called like safety locks, so it does not go flip in the other side. And because of abuse of the usage of it, it's complicated. Now we have locks front and locks in the back to make sure that with time, if you lose friction, that's not a hazardous problem. Now this is, and then you have the hydraulic knee, which it's just a mechanical system, right? And it's simple to design and cheap. Now this device, it's a class 2 because it's not life-sustaining, but it's life-threatening if it fails because of falling and other problems. Now the shank, we have something called crustacean, and then you have the modular shank, which is a pylonian exoskeleton. Oh, sorry, endoskeleton. What does that mean? Endoskeleton mean that the load-bearing part is this one in the middle, the pylon, and the outer shell is just cosmetic. We call this endoskeleton. Now, so before we have this technology, we had something called exoskeleton shanks, which is all hard plastic, and you don't have something in the middle. Now, the problem with exoskeleton prosthesis is that based on the surgery and the nature of the subject, sometimes there is tilting in the lower extremity. With the endoskeleton, you can account for that, and that's helpful. That's really good for the subject. Then you have the foot ankle. Now, I'm passionate about the foot. I'm really passionate because the foot is actually, especially for sports athletes, is the most crucial part of your lower extremity. So we have something called sack foot, and if I remember, it's soft, articulated, cushionated heel foot. That's what it's called. So there's a lot of things in it. And then you have the same thing, the sack, but it's multi-axis foot, and you have single-axis foot. Now, one of the exercises that I would like to do is I would like you to find out the name and the address of companies that make foot ankle assembly. That's what we call foot and ankle assembly. We're going to do it later on in the class, but what we want to do is that we would like to know who is building these, where. Your foot and ankle assembly is one of the most important things that you need to know. Designed to provide base of support. We're going to understand how to find the base of support for subject, and hopefully our volunteers, when we will look at how that base of support is changing with their lower extremities. Also, we would like to have shock absorbance so that you don't damage the lower prosthesis. And we like to have push-offs. Now the designs are actually very advanced and very thoughtful that it can actually give you store energy and give you energy. This lower part, which is the assembly. And also you need to make sure that you are considering uneven terrains if someone is going to use this. 4 general categories: Non-articulated, which means that we don't have a joint. It's just flat piece of plastic. And if we said articulated, it means that there is movement in the joint, in the ankle itself. And it could be single axis or multi-axis movement. And then we have something called elastic keel, and that's the one that stores energy and then gives back when you step in. And then we have dynamic responses. That's also more energy storage, but in a different way for them. And then one of the most so it's not soft, it's solid ankle cushion heel sack. Oh, sorry, it's a solid ankle cushion heel foot, and it's cheap, it's simple, and it's durable. However, if the subject is active, it's not going to help much with that. Now, engineers, what are we going to do? We would like to look at hopefully if we were successful of getting some samples from people. I have a 3D scanner. We're going to use the 3D scanner to scan those parts and open them in SolidWorks. And then try to see, your job is to design, right? So you need to look at them. Let's first of all see if we can get parts. If we can't, we're going to use the one that we have there, and we're going to scan it, do 3D scanning for it here in this lab, and then open it in SolidWorks, and then see if we can modify things and how we are to do with the object. Yeah, I have high hopes that we will be doing a lot with the foot and ankle assembly this semester. Now the shank is the part that is between the knee and the foot, right? That's the shank, and it's connect the socket to the ankle and foot assembly. So the two most important parts are the socket and the ankle, foot and ankle. Now the shank is just load-bearing component, but it has to be hard, and the mechanical properties should be appropriate to hold the weight of the subject. And it's a central pylon, narrow vertical support inside the foam. If that's, remember, this is called endoskeleton, right? If it's inside. System allow for adjustment, realignment. In exoskeletal shank, the strength is provided by the hard outer shell, and it's not, you don't have anything you don't have pylon inside. The exoskeleton are more durable, but the endoskeletal are more flexible and provide you with more functionality for them. For fixed alignment and adjustment is good. Suspension, there's a lot of text here, but the suspension it's another important part, and the whole idea is that you need to make sure that it is securing your prosthetic, right? There are different things that you can use. For transtibial, remember transtibial is the cut below the knee, right? So if you have transtibial amputation, we can use sleeves because it's not a large prosthetic. It's lighter than, let's say, mid femoral or transfemoral. So you can use sleeves. You can use belt and strap, lacers. We have suction styles, so you can have a device, and the socket will actually with the gel, and then you will have two pieces. One piece that is placed on the residual limb, plastic, and another piece and the socket itself, and then you will have a pin coming out, and you can do negative pressure so that those two pieces are locked together. So that's actually used, especially with children, because they're not heavy, and they keep moving, they're active. So a suction system is much better for them to have than a traditional belt and
Is suction enough to cause patients to stop?
Yeah, if you need always to check every day. If there is any problem with pressure and strain, we should stop. But usually, because you have two pieces, one piece that is like a sleeve, plastic, and then the other one so the suction is not between the skin and the socket, it's between two rubber pieces, That is much more comfortable actually for yeah. But still, it's a problem. We need to be careful about it. Now, how can we fix this, or can we uh, monitor this by having load sensors, right there? That's an add-on I would love to see and test with those. The idea about this class is we're talking about ideas, right? And then in the future, you can probably try and test some of these as you want. Yes, there's a lot of things here. Belt and strap method is something that I like. Yes, but it depends on the amputation and how active the person is. Yeah, so we have sleeves that fit on the residual limb, and then the pin locks into. So you can have also pin. So you can have, let's say, a sleeve, right? With the sleeve, there is a pin coming down from it, and then the socket has an opening for that pin. So when we put the residual limb in the socket, it just locks. And then there is a pin outside, like a push button. You can push on it, and it releases the pin. So that's another way. So the suction and this pin lock system is things that people do. Okay, socket. Now, if someone asks you which one of them is actually really a biomedical engineering component, it's the thing that interacts with the biological living system, which is the socket, right? All of the other ones, mechanical engineers can work on them. But the one that interacts with the body, that's that's absolutely 100% biomedical engineering component. So it enables the connect and fit of the stump. Stump is the residual limb, whatever left. And we would like to work with someone who does not have a disarticulation, at least have some piece of them below the joint available. Most important one, fit is crucial. That's why we would like to add load sensors. If the socket is uncomfortable, that's a big problem, and people will stop using actually the prosthesis. They feel pain. They will go multiple times to fix this. It's not going any better. They will stop using it, and we need. And then the problem is not that they're not going to be using it, and the problem is the medical complications, the secondary complications because of the amputation, and not using the lower extremities. Contoured sockets fit closer to the remaining bone, muscles, and that's a tricky thing because each surgeon will have a different way of suturing, and then you will have a different stump, and then some of them get swallowing quickly. A lot of water can accumulate if they're not active. So there's a lot of things that goes into this. And then, you know how they're designing the sockets? They actually do use traditional ways of creating a mold, right? And then do some casting for the plastics. I like to use 3D scanners. So bring the subject, expose them to a 3D scanner, then I have 100% the contouring of them, and it's digital. And then you build your socket. But it's because it takes skill and knowledge in using the devices. They don't use it in the clinics that they create this or build that. But I think it's going to change quickly. Now, prosthetic rehabilitation. Now, physical therapy is about the range of motion, strength, bed mobility, transfer from one place to another place. It takes in the initial rehabilitation period. Remember we talked about you cannot do rehabilitation or provide prosthesis for a subject immediately after the injury because there are 4 stages of the psychological state of a subject. We like to build temporary prosthesis as quickly as possible so that to limit the swallowing of the stump, the residual limb. If we lift it, a lot of water will accumulate in it, and it will become really hard to deal with. So we have temporary prosthesis. Socket should fit securely. Prosthesis length should match the length of the other leg, the intact leg. The patient must learn how to properly put on the residual limb socket and itself. how they use it, and also put the loads on that thing. That's part of something called prosthetic rehabilitation, not physical therapy. But if it's swallowed, there are a couple of problems. We need another socket, right? But the other thing, the load on both sides of the body is different now. And that's going to cause imbalance if you didn't account for it in the design. And I don't think we have the luxury that for each subject, you will have the time to do multiple of these. So it's a tricky situation, actually. Okay, role of physical therapy. So what are they doing? Are they supposed to? We designed something. We gave it to them. What are they going to do? They need to ensure that the inside of the socket is smooth and that all joints move freely. It's not your job. It's their job. Evaluate the prosthetic function immediately and over time. Remember when we talked about the 10-minute walk and the 3-minute walks and this L shape and mobility? All these tests should be done with and without the prosthetic. Make assessment of gait and watches the compensation. See how the subject is moving. It's energy consuming to use a prosthetic. Give patient instruction regarding proper care and maintenance of for each individual. Now this is part where we can get involved in to teach them how to assemble it, how to clean it. If there's something wrong with it, what they should be doing. Change the setting, for example, the friction of the knee. That's something we need to do for them. Training, individual begin with learning and to keep their body stable, and that is where the force plates comes in. That's why I love the force. I love the force plates the most, actually. It's markerless biomechanical system, but it gives you a lot of data, a lot of information, and we're going to work with that. Practicing standing balance on and both legs. Individual must be taught how to transfer to and from surfaces. And what do we, standing from a chair and then going to the bed, right? These are things. Position, kneeling, squatting, and manage fall. So we have labs that they will have a treadmill, right? And the subject is with harnesses on the ceiling, and we expose them to different slipping conditions and see how they are going to manage with the fall. Canes, quad cane. So you need to see how they're going to use other assistive technology with the prosthetic itself. And then patient motivation. I think we need to do more in empathy as engineers and to see how can we strengthen this part, the motivation of the patient to do that. Okay. Thigh prosthesis, this is below the knee, right? What do you call this? The amputation. Transtibial. Then you have the knee, this articulation, the knee is gone, right? They have above the knee, which is transfemoral. And then you have the hip articulation. Now, most of the new designs are something like this. You have the pylon inside, that's the endoskeleton, right, of it. And there are a lot of designs for the suspension system that people are using. Now, it looks like it's a heavy device, but actually they're using a lot of carbon fibers and different plastics. It's light, but it's very strong. Now, hopefully we will be able to, in this class, Institute course class, if we were able to have a couple of subjects to get some data from them, just the force plate, that's a huge success for us. And that's my plan. Now, tibial, transfemoral, partial foot. Now, these are plastics. It does not give you a lot of base of support, but it's just aesthetic for the subject. And you'll have this is a complete prosthetic feet. That's the solid articulated, right, cushion heel. Oh, solid ankle cushion heel. Solid ankle cushion heel prosthetic. Now, this is the one that you have. It's like an endoskeleton, but this heel it absorbs the shock, and that's a real cool design. But The coolest designs are actually those ones. See this one and that one? They store energy and give it back to you, the elastic. And as I told you, having a prosthetic is energy consuming. Any way that you can give them energy, the subject when they walk or run or do any activity, that's a very substantial advantage for them to have, advantage for the prosthetic. So we would like to look at, call people, send emails. So we did this, me and Dana, to get a company to give us memory, storing memory alloys, which are metals. The companies, if you're a student and you tell them I'm working on a project and I want to test, they will send you samples. Heck, they send samples for YouTubers to unbox stuff, right? And nobody's doing this for biomedical engineering. Or any medical device. They would love to do this. There is a lot of, new materials and polymers that is even much better than the original, the previous ones. I know, because there's a moving part, you can think that there is a lot of tear and wear for that part, but it's designed in such a way that is really, really good, and it's tested. Yeah, I love these, and I think as engineers we need to be thinking about these innovative, solutions for them. So hopefully we're going to get some. You can search, single and multi-axis foot and ankle assembly, and check who's selling those, the company, and just send an email to any contact us email they have, and tell them I'm a biomedical engineer, I'm a senior biomedical engineer, I'm working on a project in a rehabilitation engineering class. Can you donate one of these assembly parts for us to do testing on it? That's it. They said yes, that's good. Said no, it's fine. For the end of the year, next company. Oh, you can't believe how many people told me no in anything I do. I just don't stop. It's just horrible. Okay, so this is your job, guys, in the future if you want to do this. Now, current technology manufacturing, this is what I don't like. I like 3D printing. I like to be able to build a foot and ankle assembly in 3D. So we have a company, a website that can give you the code or the design, the drawing, and Ben said he's going to help us in print out. So I'm going to share with you a link next time for foot and ankle assembly, and we're going to do 3D printing it, but it's components, pieces, right? We need to assemble it together, and that's something we'd like to do in one of the classes, and see if we can build that foot and ankle assembly. Now, people are using different materials, carbon fibers. I like to do 3D printing, and I would suggest from you guys to refresh your information about SolidWorks, SolidWorks, and how to do. Because if you do 3D printing or 3D scanning, either way you're going to use SolidWorks in your work, in your life. So that's a suggestion and encouragement for you to go back and try to practice something. I don't know if you have the assignments from, that was a long time ago, EGE 130, long time ago. But believe me, guys, if you want to you want to get really good in these type of tasks and employment opportunities, let's say that SolidWorks is key, really key in doing that. So we're looking for a lighter and stronger materials all the time for prosthetics, and then you need to make sure that you are doing something that is realistic. So what we are doing, we can develop now materials with similar skin tone. We need to make sure that we are using a lot of electronics, especially controllers, Arduinos. That's what we need, and sensors. So when we talk about electronics, it's Arduinos and sensors. That's what we want to do. We're going to talk about the myoelectric control limbs and electrical, externally powered limbs and myoelectric. Myoelectric limbs are prosthetic prostheses that they are activated and controlled by the muscle activity of another part of the body. So you have sensors, surface muscle activity, and then you control the prosthetic. So let's say if I have, let's say a transfemoral, part of the my femur muscles are still there, so I can do contraction to that muscle, and then I can move the leg front or back the prosthetic. We're going to talk about those more. So convert muscle movement to electrical signal, and then that's your control. Yes, it's direct control. Computers are also being extensively because of the Arduinos we're going to be using. Now, this is traditional technology that they're mentioning here. I would like to see more sensors, more add-ons, more controllers in designing the prosthetics. Now, we are in an educational setup, and so it doesn't have to work 100%, but at least to try to do something like that. Make sense? We're good with that? Okay. I'm going to finish that here, but I want from you to go online and search for the companies who build the solid ankle cushionated heel. Search foot and ankle assembly companies, and see if you can find someone in the United States, or who knows, maybe in Ohio, Indiana, Pennsylvania, the Midwest, and see if we can have their contact info.